Hi dear children, I welcome you to another session of dual nature of radiation and matter. In the last class we have discussed about the Einstein's photoelectric equation and how that experimentally verifies the existence of particle nature. That was done by Sir Millikan. In today's class we are going to study about the particle nature of radiations, that is photon picture. This is not a new word for you because you have learned about photons in chemistry associated with the black body radiations, Planck's quantum theory. Now we are going to study the corresponding aspect of that in physics. Now we are at the moment. So when we studied the chapter wave optics, the theory was fluctuated only to the wave effect because the existing phenomenon like reflection, refraction were reflection and refraction was successfully explained using the wave theory. Then we have studied about interference and diffraction or diffraction. That can be explained only by the wave theory. Then we concluded that radiations are only wave nature. Now when we come to this chapter, that is chapter number 11, dual nature of radiation and matter, while discussing the concept of photoelectric effect, we have seen that yes, wave nature cannot explain photoelectric effect. Wave theory was an absolute failure in explaining the wave theory of the photoelectric effect. So we shifted our attention to the particle nature of radiations, and what we believe now is particle nature of radiations, right? We are believing now in particle nature of radiation. So we are going to start our discussion on the particle nature of radiations and the concept of what is called photons. So what are photons? Photons means what? Photons. So in simple words, what you know is photons are the quanta of light. Photons are nothing but the quanta of light. And the question then comes, where do the quantum picture comes into play? That is what is very important. The quantum picture of radiations is coming into play in the interaction of radiation with matter. In the interaction. So in the interaction of radiation with matter, the quantum picture comes into play in the interaction of radiations with matter. So according to the photon picture, what is actually a photon? Answer is very simple. In the interaction of radiation with matter, radiations behave as if it consists of particles called photons. I repeat. In the interaction of radiations with matter, radiations behave how? As if it consists of particles called photons. I repeat once more. In the interaction of radiations with matter, radiations behave as if it consists of particles called photons. That's an important point. So, where photon picture comes into play? Where photon picture comes into play? It comes into play when radiations interact with matter. Photon picture comes into play when radiations interact with matter. Now the question, what is the energy of a photon? Answer is, energy of a photon is h nu. What is h? Planck's constant. And what is nu? The frequency of the light, frequency of the radiation. So energy of a photon is h nu. This can also be written as hc by lambda. It's h nu, otherwise hc by lambda. Then the question comes, what is the momentum possessed by a photon? Momentum has a formula, it is E by c, energy by c, or this is equal to h by lambda. H by lambda, momentum of photon is h by lambda. E by C, that is h by lambda. Right, so then the question, what is the mass of a photon? So let me tell you an important point. Photons do not have rest mass. The rest mass of photons is equal to 0. The rest mass of photons is 0. Then what mass they possess? They possess what is called dynamic mass. And dynamic mass of photons is h by lambda c. H by lambda c, that you can get from the idea of momentum. Momentum P is equal to mc, that is equal to h by lambda. mc is equal to h by lambda, so m is equal to h by lambda c. This is the dynamic mass of photons. Right, so that is regarding the mass of the photons. I have to say dynamic mass because they have 0 rest mass. They do not have rest mass, but what they have is they have dynamic mass. Photons have dynamic mass, their rest mass is equal to 0. Ready? This rest mass of photons is equal to 0. Yes. Then coming on to the next area, that is regarding the power. So power is equals energy divided by time. Now this can be written as capital NH nu, or that is capital NHC by lambda. What is capital N? Number of photons per second. So capital N is nothing but number of photons per second. The number of photons per second is called capital N. So number of photons. So when you say a certain power of the light, so in that power, when it is incident on a certain surface, so the power of that light is equal to NH nu. In that N, it is the number of photons per second. Now then comes the idea of what is called intensity. What is the intensity? Intensity is power by area. Right? Intensity is energy per unit area per unit time. So energy by time is power, so it's power by area. I will say this is NH nu and this is NHC by lambda. What is N here? N, number of photons per unit area. Per unit area. Per unit time. So understand these terms clearly, I tell you. It's a number of photons per unit time, unit area per unit time. It's a number of photons per unit area per unit time, that is small n, whereas capital N is number of photons per unit time. So this is very, very important, I am saying. Now let us come to our idea of, so we have got such a graph with the photoelectric effect. Small I, capital I. And we have seen that for a given frequency, small I increases with capital I. Tell me what may be the reason for this. Very, very simple, children. That is, when intensity increases, again when intensity increases, number of photons striking the surface increases. Repeat, what happens when intensity increases? When intensity increases, number of photons striking a surface increases. When number of photons striking a surface increases per unit area, number of photons striking per unit area of a surface increases, which proportionally cause ejection of more and more electrons, right? Which proportionately increases the ejection of more and more electrons. So photocurrent correspondingly increases. I'll repeat once more. When intensity increases, number of photons striking increases. When number of photons striking increases, number of photoelectrons ejected also increases. So which increases? When number of photoelectrons increase, current I is equal to, according to our knowledge, it is equal to N dash E by T. So I have to say that I proportional to N dash, where N dash is the number of photoelectrons ejected. but capital A proportional to small n. Intensity increasing means number of photons striking increases. When number of photons striking increases, number of photoelectrons also will increase, right? So that's the reason why I tell you that the photoelectric current is directly proportional to the intensity. So I hope that picture is clear to you. Okay, just joking, nothing more than that. So these are a few ideas you have to understand regarding the basic formula of the photon picture of light. Now the topic is not over, because what about the charge of a photon? Charge on a photon. Very simple. I will say photons are chargeless. Photons are chargeless. So it does not have positive charge. It does not have negative charge. So telling you photons are chargeless. Question: if they are chargeless, can they be deflected by both electric and magnetic field? When they do not have a charge, will they be deflected by both electric and magnetic fields? My answer is, what is your answer? Will they be deflected by both electric and magnetic fields? Yes, yes, yes. They cannot be. They will not be deflected by any electric field, neither electric field nor magnetic field, right? So they cannot be deflected by both electric and magnetic fields. Very simple. Now the question: what kind of collisions do photons undergo? So collisions, what I have to say? So what type of collisions do they undergo? In all such collisions, total energy, that is a common rule for collision, total energy and total linear momentum are conserved in every collision. But very important point you have to understand is that the number of photons is not going to be conserved. In a collision, some photons may be absorbed and some new photons will be generated also. Because photon is energy. Suppose that a hydrogen atom is absorbing a photon, say of energy 11 electron volt. You might have studied that, out of which 10.2 electron volt will be utilized for a transition. Right? That is only what hydrogen can take for a transition from ground level to first excited level. So it has taken 10.2 electron volt for a transition. So what happened to 8.8 electron volt? The remaining 0.8 electron volt will be utilized for it will appear as the kinetic energy of the hydrogen atom. That is one way. Or otherwise, if I say it has got, so energy of the photon is equal to something like 12.1 electron volt. So if it has, so this is only one photon, right? Now what happens here? So if it is absorbed by a hydrogen atom, I will say it will be n is equal to 1, n is equal to 2, n is equal to 3. So this many transitions will take place. So a hydrogen atom will make a transition from here to here. So during the de-excitation, this is photon number 1, this is photon number 2. So only one photon absorbed, 2 photons are released, right? So that's what I mean, that the number of photons, in the collision, the photon number never remains conserved. So new photons may be generated in the process. In the similar way, what I'm saying, so new photons we may get or we may lose photons. So photon number is not going to be conserved in the case of collision of a photon with a particle. So these are the ideas I want to say regarding the photon picture of radiations. Now we are here with a situation that radiations have dual nature. The wave nature was successfully explained with the interference, diffraction and polarization, the wave property. And transverse wave nature was explained using polarization. So wave theory was used to explain interference, diffraction and polarization, which cannot be explained with the particle theory. Whereas photoelectric effect is a consequence of the particle nature of radiation, which cannot be explained by wave nature. So let me conclude now. Wave nature explained the phenomena like interference, diffraction and polarization. Particle nature explained the properties like phenomenon like photoelectric effect. Particle nature explain the property of a phenomenon like photoelectric effect, and we can explain reflection and refraction using both the theories, I have to say. That is the idea regarding the photon picture. Now we will move to example number 11.1. Read the question in 11.1. Monochromatic light of frequency 6 into 10 to the power 14 Hz is produced by a laser. The power emitted is 2 into 10 to the power minus 3 watt. What is the energy of the photon? Very simple. Energy is equal to h nu. This is 6.6 into 10 to the power minus 34 multiplied by 6 into 10 to the power 14 Hertz. So this can be multiplied to get approximately. So approximately you will get this answer as 4 into 10 to the power minus 19 joule. Approximately this will be equal to 4 into 10 to the power minus 19 joule. That is a very simple calculation, right? Now the question, how many photons on an average was released? Number of per second. So it is per second, so that is capital N. We know that capital N is power divided by E, right? We got power is equal to N h nu. This term is nothing but energy. This is N into capital E, or N is equal to power by energy. This is 2 into 10 to the power minus 3 divided by 4 into 10 to the power minus 19. This is 0.5 into 10 raised to 16, or this is 5 into 10 to the power 15. So these many photons are released in 1 second. The number of photons released on an average per second is this value. Okay, that is the answer to. These are the answers to our question. Example number 11.1. It's a pretty simple calculation, let me tell you. Let's read the question now. Work function of cesium is 2.14 electron volt. Find the threshold frequency, and second part is wavelength of the incident light. The stopping potential is 0.60 electron volt. So first part is very simple. Given work function phi is equal to 2.14 electron volt. And according to the Planck's condition, we can say this is equal to h nu 0. Since this side of the equation is in electron volt, we need to find the value of h also in electron volt. So this is 6.6 into 10 to the power minus 34 joule second. Correspondingly, we can say this is equal to 4.125 into 10 to the power minus 15 electron volt second. That means nu 0 is equal to phi divided by h. This is 2.14 divided by 4.125 into 10 to the power minus 15 Hertz. So 2.14 divided by 4.125 into 10 to the power minus 15 Hertz. This value is approximately 0.52. Approximately, I am saying, into 10 to the power 15 Hertz. So this will be something like 5.12 into 10 to the power 14, 5.2 into 10 to the power 14 Hertz is the answer we are expected to obtain. I hope this part of the problem is clear. Yes. What is now the second part of the problem? We are asked to find out the wavelength of the incident light. Okay, so let me wipe off this part of the board. So work function is given. Stopping potential is given as 0.60 electron volt. According to the Albert Einstein's equation, EI is equal to 5 plus EV0, right? It is 5 plus EV0, which gives me Hc by lambda is equal to, the value of 5 is 2.14 electron volt plus 0.60, this E, 0.60 volt only, my fault. This is also volt, not electron volt. So 0.60 electron volt. So this will come out to be 2.74 electron volt, right? 2.14 plus 0.60, it is 2.74 electron volt. From here you can calculate the value of lambda, right? So lambda is equal to Hc divided by 2.74 electron volt. What is the value of Hc we told us today? In last video we said Hc is equal to 12400 divided by 2.74. This much angstrom you will get the answers. So now I request you to divide this and find the answer and send back to me. Here comes the discussion of example number 11.3. The wavelength of light in the visible region is about 390 nanometer for violet, about 550 nanometer for yellow-green color, and about 760 nanometer for red color. Find the average energy of photon in each case. That is very simple question, as now we can see. This is for violet. So let us start for violet. What will be the energy is equal to Hc by lambda. For everything energy is Hc by lambda, which can be calculated as 12400 electron volt divided by 390. 12400 divided by 390. So this is about 390. So 10 can be cancelled. So 124 divided by 39. So 39 into 3. 40 into 3 is right. So this can be written as 117 plus 7, right? 1170 plus 70 divided by 39, right? So this calculation will give you, yes, this is equal to 3 plus the 70 divided by 39 is 1.39, then 31. So rather 70. Oh, sorry, this is not 00, it's just 10 enough because it's in nanometer. So this 0 is gone. 117 plus 7, right? 117 divided by 39 is 3. 7 divided by 39 is 0.1. Then another 3 comes. About 9, right? So this will give you the answer like 3.19 electron volt. This is the energy for violet color. Now for what is the next color? Yellow green. For yellow green, let us make this calculation is equal to 1240 divided by 550. So I'm just doing it as 124 divided by 15. So I'm going to just rearrange this value for the ease in calculation. 110 divided by 55 plus 14 divided by 55. So 110 divided by 55 is 2 plus 14 divided by 55 will be 0.2. Then there is another 3 coming. Around 0.2, right? Around 3 coming. 14 by 55, 140 divided by 110, 35. Or rather approximately 6 we can say. So I'm just going for 2.25 electron volt, or it's an answer between 2.25 electron volt and 2.26 electron volt. Now for red color. For red color, this energy is equal to how much? 124 divided by 76. Now I'm going for the direct calculation. 0 is avoided. So this is 1 point. So 176 plus 48 divided by 76. This also divided by 76. Now 76 by 76 is 1 plus 48 by 76. Around 6.6. 76 into 0.6 is 45.6. 45.6, there is 0.24 remaining. Right, sorry, 2.4 remaining. So that will give you like 3. I'm just going for a rough answer. So this will be 1.63 electron volt. I am saying 1.63 electron volt. Now there is second part of question for us. Now I am reading that part. So we got the average energies. From which of the photosensitive materials with work functions listed in table 11.1? So I am now going for table 11.1. Which and using the results of 1, 2 and 3 of a can you build up a photoelectric device that operates with visible light? Okay, obviously. So cesium. So this is 3.19. Now we can take all elements having work functions below this. We can look at the table 11.1. You can see that cesium is used. Can be used here because work function is 2.14 electron volt. Potassium we can use because work function is 2.30 electron volt. Sodium we can use because work function is 2.75 electron volt. So those elements whose work function, or those metals whose work function is less than this value can be used for producing photoelectric effect. So with the violet color we can work with the cesium, sodium and potassium. Sorry, cesium, potassium and sodium. Correspondingly, what is possible here is only cesium. Why? Because the work function of potassium is 2.30, which is greater than this incident energy. So what that is possible is only cesium. What about red? What about red color? So this way energy is 1.63, which is less than that of cesium. So no photoelectric device can be operated under this with this wavelength. I would say, sorry, this energy I would say. So we cannot use red for this one. So with red color nothing is possible. I hope this is the idea regarding example 11.3.